Hey guys, we're back with the trigonometric functions and properties of them. We are learning about all of the different trigonometric identities, which are statements of equality that you can interchange in a problem. So we have the reciprocal trig identities, and we know that cosecant is the reciprocal of sine. We know that secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. And remember, these reciprocal identities, they work both ways. If cosecant is the reciprocal of sine, then sine is the reciprocal of cosecant. And that is something that could be interchanged in a problem. If secant is the reciprocal of cosine, then cosine is the reciprocal of secant. And if cotangent is the reciprocal of tangent, then tangent is the reciprocal of cotangent. And these are all statements of equality that we can interchange in any math problem. All right, then we have our quotient identities where tangent is the sine divided by the cosine and cotangent is the cosine divided by the sine. All right, and then we have our really important Pythagorean identities, which all come from the equation of the unit circle. And the equation of the unit circle said that x squared plus y squared equaled 1, because it's centered at 0, 0 with a radius of 1. Well, remember, on the unit circle, the x-coordinate represented the cosines of all of those angles. The y-coordinate on the unit circle represented all the sines of all of those angles. So then we could substitute x with cosine, and you get cosine squared theta, plus we can substitute y with sine squared theta, and it equals 1. And that is the first Pythagorean identity. And then we get all the other Pythagorean identities just by manipulating him and moving things around, all right, and creating more statements of equality. First one is, if I got cosine squared theta by itself, I would minus him over. And now you have cosine squared theta equals 1 minus sine squared theta. All right, I could get sine squared theta by itself by minusing cosine squared theta away. And now you have sine squared theta equals 1 minus cosine squared theta. So these are statements of equality that can be interchanged in any math problem. All right. Now I could go back and I could just start dividing everything by cosine squared theta. Divide this by cosine squared theta, I get 1. Plus divide this by cosine squared theta, I get tangent squared theta. Divide this by cosine squared theta, and I get secant squared theta. All right, I can solve this identity now and get tangent squared theta by itself just by minusing the 1 away. And then you get another identity that says tangent squared theta is equal to secant squared theta minus 1. I could come over here, I could minus tangent squared theta to the other side, and then I would have secant squared theta minus tangent squared theta equals, the only thing left would be 1. I could come over here and I could minus secant squared theta to the other side, and then I would have tangent squared theta minus secant squared theta equals -1 would be the only thing left. So again, these are all statements of equality that you could interchange in a math problem. All right, well then I could go back to the original Pythagorean identity. I call him the mom and dad. He's the parent of all of your Pythagorean identities. And I could go through and divide by sine squared theta. So if I divided this by sine squared theta, I would have cotangent squared theta. Plus, if I divided this by sine squared theta, I would get 1. And it would equal, if I divided 1 by sine squared theta, I would get cosecant squared theta. All right, I could come over here. I could get cotangent squared theta by itself just by minusing the 1 away. And then I would have cotangent squared theta equals cosecant squared theta minus 1. And then you could come over here and start playing around with these ones. I could minus cotangent squared theta to the other side, and I would end up with cosecant squared theta minus cotangent squared theta equals, the only thing left would be 1. And I come over here, I could minus cosecant squared theta back to this side, and I would have cotangent squared theta minus cosecant squared theta equals -1 would be the only thing left. So again, these are all your Pythagorean identities, and you could use them to interchange any one of these in a math problem. So if I had 1 minus sine squared theta in a problem, I could take that out and put cosine squared theta in its place. Okay, these are all statements of equality that we can interchange. All right. Well, there's a couple more identities that you have to learn, and they have to do with even or odd functions. If you remember what an even and odd function is, even and odd functions are defined by what kind of symmetry they have. So we have to review our rules of symmetry. All right, so what does it mean to have symmetry? Well, think about it. If you take something like an ordered pair and reflect it over the x-axis, right? If you reflect something over the x-axis, then what changes? The y-coordinate. So then it becomes the point x negative y, or the opposite of y. So if your graph has symmetry to the x-axis, then both of these points will live on its graph. The point xy will be on its graph, and so will the point x negative y. All right, well, what if you have symmetry or you are reflected over the y-axis? Well, if you take something and reflect it over the y-axis, then the x-coordinate changes, and then it becomes the point the opposite of x comma y. Okay, so if your graph has symmetry to the y-axis, then both of these points will live on his graph. For every xy that lives on his graph, there is a negative xy that lives on his graph when you have symmetry to the y-axis. All right, and then if you remember, if you reflect a point over or through the origin, then the point becomes, if you go through that origin there, right through the origin, then it becomes the opposite of x and the opposite of y. So if a graph has symmetry to the origin, both of these points will live on his graph. For every xy that is on his graph, there is the opposite of x and the opposite of y that lives on that graph. All right, so by definition, even and odd functions were defined by what kind of symmetry they had. One of them had to have symmetry to the y-axis, and one of them had to have symmetry to the origin. Well, which one was which? Well, let's see. An even function, by definition, is when x goes into the function, y or f of x comes out, right? That's normal. X goes into the function, and then y comes out. So I can make that ordered pair. X went in, and y came out. Well, if you are an even function, then when the opposite of x goes into that function, the same y, f of x value still comes out. So when the opposite of x goes into that same function, the same original y coordinate came out. So now the opposite of x went in, and the same y coordinate came out. So that would be like the point 2, 3, right? 2 went into the function, and positive 3 came out. Well, when the opposite of 2 goes